for more than a decade a cross-disciplinary team of chemists and physicists in art sciences at Washington University in St. Louis has been chasing the atomic nucleus. With progressive studies, they moved up the element chain to calcium-48, an extremely rare solid commodity that has more neutrons than protons and, as such, carries a hefty price tag of $100,000 per gram. It is a quirky material, with this particular study taking Washington University chemists Robert J. Charity and Lee G. Sobotka from Duke's Triangle University's Nuclear Laboratory to the Department of Energy's Los Alamos N.M. National Laboratory. If you leave it on a table, it turns to powder, said co-author Charity, a research professor of chemistry and art sciences. Calcium oxidizes very quickly in air. It was a worry. Ultimately, 3 grams of circa 48 helped to produce a double-edged finding for Charity and co-author Willem H. Dickoff, professor of physics. The team discovered both a framework to predict where neutrons will inhabit a nucleus and a way to predict the skin thickness of a nucleus. In the research published November 29 in Physics Review Letters, they predicted how the neutrons would create a thick skin, and that this skin of Ca48 to 3.5 femtometers FM in radius measured 0.249–0.023 FM. To convert that into centimeters, it would measure 2.49 times 1014 centimeters. The researchers say the key finding is that the skin is thicker and more neutron-rich than previously believed. That links us to astrophysics and, in particular, neutron star physics, Dickoff said of the research results. The Los Alamos experiment was critical for the analysis we pursued. In the end, because it has this additional set of neutrons, it gets us to information that helps us to further clarify the physics of neutron stars, where there are many more neutrons relative to protons. And it gives us the opportunity to predict where the neutrons are in circa 48, Dickoff said. That is the critical information, which leads to the prediction of the neutron skin. For Charity, Dickoff and co-authors Hossein Marzouk, Ph.D., 15 Electra in physics at Truman State University in Kirksville, Mo, and Mac Atkinson, a Ph.D. candidate in physics at Washington University. The chase continues. They watch with interest as circa 48 is scheduled to undergo the cleanest skin thickness test available via the Electron Accelerator at the Thomas Jefferson National Accelerator Facility in Newport News, Virginia. Moreover, they proceed to move up the element chain of neutron-rich nuclei to what Charity called the famous nucleus of lead 208. Michael Keim, a senior in physics, is spearheading a study of lead 208. This graph basically shows where the protons are more solid lines exp and ch, and where the neutrons are dotted lines n and w in the nucleus. The neutrons are located in the thick skin, where the dotted lines separate from the solids. To be precise, the experimental maroon staggered line and fitted black charge distribution are the solids, and the neutron matter distribution blue and the weak charge distribution red hashes are the dotted lines. Graphic the authors, it will give us an experimental handle on whether our analysis is really predictive. Dickoff said, "We think we have a good argument why we think it has a thick skin. There is a large group of people who predict a smaller skin. This is directly relevant for the understanding of the size of neutron stars. It is not yet crystal clear how big a neutron star is, its radius." Dickoff how they made their analysis and reached this predictive framework as part of their decade-long pursuit as well. Their chemistrophysics group subscribes to dispersion relations, which Sobotka, who is a professor of chemistry and of physics, explained simply, it's what tells you not to laugh before you are tickled. That means causality is properly taken into account. In short, they analyze all energies simultaneously rather than focusing on one single energy. Since first publishing together in 2006, they have used the dispersive optical model DOM, developed a quarter-century ago by Claude Mahoxa, a nuclear theorist from Belgium. They expanded upon it across energy domains and isotopes, so they could attempt to predict where the nuclear particles are. We had to make the technical step to include the sensitivities of particles. Dickoff said. He used his hands to illustrate the center and then the rest of a nucleus. If they're here, they were also influenced by everywhere else, which we call non-locality. Without that, you cannot make these predictions. Heavy neutron-rich elements behave differently. So this team keeps ascending the heavyweight class circa 40, circa 48, lead 208. How far can you go out along an isotope chain until losing neutrons? Charity said. It gives them skin in the skin game. Charity, when you put extra neutrons in, it doesn't like that, right? Charity said of the atomic nucleus. It has to figure out how to accommodate these extra neutrons. It can put them evenly throughout the nucleus, or it could put them on the surface. So the question is this force stronger in the low-density region of the nucleus or weaker? We know where the protons are, Dickoff added. That is well established experimentally. But you can't do that easily with neutrons. I simply want to know what a nucleon, a proton or a neutron, is doing. How is it spending its time? Nucleons are more interactive. They do other things than sit quietly in their orbits. That's what this method can sort of tell us. The non-local DOM framework, a decade plus in the making, uses computer modeling and computations as well as the lab experimentation. It allows them to make a prediction that is well-founded and taken seriously, Dickoff said. Next, we will have a measurement for lead 208. This study was funded by the U.S. Department of Energy, Division of Nuclear Physics Grant DEFG 0287ER40316 and National Science Foundation Grants PHY 13044242, PHY 16133362 and PHY 15209171.